Section 20 of the National Geographic Magazine, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. An Expedition Through the Yukon District by Charles Willard Hayes, Part 4. Volcanic Phenomena. Active volcanoes. Volcanic activity in the United States within historical times has been confined wholly to Alaska and, excepting somewhat mythical eruptions of Mount Calder on Prince of Wales Island in 1775 and of Mount Edgecumbe in 1796, it has been confined to the southwestern extremity of the territory. The most easterly known crater which shows any activity at present is Mount Wrangell. This was observed for several days during August, 1891, from Taral, at the confluence of Chittenah and Copper rivers. It lies about 55 miles nearly north of Taral, and only the top of the mountain, a sharp black cone, appears above the intervening broad snow-covered dome of Mount Blackburn. From this cone masses of densely black vapor were constantly rising. At intervals of about half a minute a cloudy pillar would rear itself to a height of several thousand feet, and, floating off toward the east, quickly disappear, to be replaced by another burst of vapor from the crater. No illumination of the vapor was noticed at night, and so far as I could learn from the chief Nicolai, no appearance of fire was ever seen. According to the diary of John Brenner, a miner who spent the winter of 1884-85 at Taral, the volcano was at that time in a state of somewhat violent eruption. He says, quote, "The volcano has been very quiet a good while, but today it is sending out a vast column of smoke and hurling immense stones hundreds of feet high in the air. The masses it is throwing up must be very large to be seen here. It has made no loud reports, only a sort of rumbling noise." Unquote. It is possible that an active volcano may exist east of Mount Wrangell in the upper White River basin, but our information as to its existence depends on the vague and unreliable statements of the Yukon natives, statements that may refer to Mount Wrangell. Some sharp cones were seen northwest of Lake Wellesley, and also some in the St. Elias Mountains between Klutlan Glacier and Scolai Pass. Their volcanic origin, however, could only be inferred, and any present activity would have been concealed from us by the clouds which hang about their summits. Recent volcanic activity. The most striking effect of recent volcanic activity in this region is the widespread deposit of volcanic ash, or tufa, which covers the southeastern portion of the Yukon basin. This deposit was first noted by Schwatka in his reconnaissance of 1883. It was more fully described as it occurs on the Pelly and Lewis by Dawson in his report of the Yukon expedition of 1886, and was noted by McConnell in 1887 and Russell in 1889 on the Yukon and Lewis. It was first seen by our party on Teslin River shortly after leaving Lake Acklin, and from this point northward it forms a conspicuous and nearly continuous white band in cut banks of the river nearly down to Selkirk at the confluence of the Lewis and Pelly. Where first seen the layer of tufa was less than an inch in thickness, and from this increased to a maximum of nearly a foot near the mouth of the Teslin, with some local accumulations of 2 or 3 feet. The alluvium which has accumulated upon the layer of tufa is generally about a foot in depth, but it occasionally varies from nothing to 3 or 4 feet. A foot, however, probably represents the normal accumulation of soil under the prevailing conditions since the deposit of the tufa. The first point at which the tufa was noticed in the White River basin was about 100 miles southwest of Selkirk, on the divide between the Nisling and Donjek, eastern tributaries of White River. It is altogether probable that the deposit was continuous over the whole of this country, but no localities favorable for its preservation and display were seen on the high land traversed. A layer much heavier than that appearing on the Lewis would in a short time be wholly lost on a surface almost entirely destitute of soil and composed of rock fragments of varying degrees of coarseness. In the banks of the Kluantu and Donjek the tufa does not form a distinct layer as along the Lewes, but is probably represented by certain stratified beds of white sand, which were regarded at the time as lake deposits. They are indistinguishable from the sediments carried and deposited by the river at the present time, except in being somewhat coarser. The original thickness west of the Donjek must have been at least several feet, and the increase is very marked toward the southwest. The white tufa is washed down from the steep slopes and forms considerable alluvial fans at the mouths of the ravines, closely resembling the cones of snow which form in similar position. After passing the Koidern, the narrow valleys were found deeply filled with tufa, which had accumulated from the steep mountain slopes. From the divide the upper wide river valley was seen stretching 40 miles to the westward, and appeared almost completely covered with drifts of snow. On reaching the valley the drifts proved to be tufa, which forms a deep mantle over the country north of the St Elias mountains, and for 20 miles west of the Klutlan forms a desert of drifting snow white sand into which one sinks from 4 to 12 inches in walking. A scanty growth of dwarf alder and blueberry bushes has gained a precarious foothold in some places, and a few stunted spruce trees grow in protected spots along the streams. The tufa extends up the mountain sides on the south, covering every surface where the slope is not too steep for it to lie, and finally merging with the neve snow, which begins about 1,500 feet above the valley, or 6,000 feet above sea level. The valley was covered with a sheet of glacial drift before the deposition of the tufa, and in consequence the drainage is very imperfect. Many small lakes and ponds, usually without outlet, occur scattered over the surface. The greatest observed thickness to which the tufa deposit attains is between 75 and 100 feet. This was seen on the western bank of the Klutlan, where there is no reason to suppose that its original thickness has been increased at the expense of surrounding regions, except perhaps by wind drift. Toward the upper end of the valley the thickness of the deposit decreases very rapidly, and at the entrance to Scolai Pass, less than 40 miles from its maximum, it appears as a narrow white streak in the freshly cut river banks, exactly as it does along the Lewes and Pelly 300 miles to the eastward. The deposit also appears to decrease in thickness rapidly toward the north, and there is no indication of any considerable accumulation on the gentle slopes of the valley or on the mesas north of White River. The gradual increase in thickness of the deposit from east to west is accompanied by an increase in the size of the fragments. As described by Dawson from the Yukon, "It is a fine white sandy material, consisting chiefly of volcanic glass, the greater portion of which has been drawn out into elongated shreds, frequently resembling the substance known as Pelly's hair." Where first noticed between the Nisling and Kluantu, it had the appearance of sand, which results from the disintegration of a rather coarsely crystalline marble, the individual fragments being from 0.5 mm to 1 mm in diameter. The average dimensions increase to the westward, and in the Klutlan valley the deposit contains many fragments of white vesicular pumice from 2 to 10 centimeters in diameter, though the greater part is much finer, perhaps from 1 mm to 5 mm in diameter. Nothing in the nature of true volcanic bombs was seen in the tufa, though their presence may have been overlooked. Taking the approximate limits of the deposit, as observed on the Yukon by McConnell, on the Pelly and Lewes by Dawson, and on the Teslin and at Scolai Pass by the writer, it will be seen to cover an oval area with a maximum thickness near the western extremity. The oval area, which is depicted on plate 18, is about 370 miles from east to west, and 220 from north to south, or about 52,280 square miles. Assuming the deposit to be in the form of a flat cone with the above base and a vertical height of but 50 feet, its volume amounts to 165 cubic miles of material. From the facts of distribution as above stated, a fairly safe inference may be drawn as to the source of the deposit. The explosive eruption which produced the tufa probably occurred in the northern part of the St. Elias Mountains, near the source of Klutlan Glacier. As already stated, it was impossible to tell whether there is any special volcanic activity in this region. One conspicuous peak, of which the top remained hidden by clouds, was pointed out by the natives as having some unusual characteristics of which they seemed to stand much in awe. The name by which they called the mountain was Nat Aj At, meaning, as near as I could make out, shape of a man. But, owing to native reticence and lack of an interpreter, it was impossible to obtain any satisfactory information concerning the mountain. Mount Wrangell has been suggested as the source of the tufa, but this is clearly impossible, as it lies wholly beyond the area covered by the deposit. The strong winds prevailing in the upper White River Valley during August 1891 were from the west, and were evidently in the same direction during the great eruption. It would be interesting to fix the date of the eruption, but it is impossible to do so with any degree of certainty. From a study of the relations of the tufa bed on Pelly and Lewis, Dr. Dawson says, "While the eruption must have happened several hundred years ago, it can scarcely be supposed to have taken place more than 1,000 years before the present time." A similar conclusion is reached from a study of the deposit in the White River basin. As already stated, for 10 miles on either side of the maximum thickness the surface tufa is unconsolidated and supports only a very scanty vegetation. But the tundra moss covers with great readiness even the most barren surfaces wholly independent of soil, so that it seems impossible this should have remained bare for any great length of time. From its position near the greatest thickness of the deposit, a vast quantity of the tufa must have fallen on the surface of the Klutlan Glacier as well as on the neve fields at its source. The fact that this has nearly all been deposited in the terminal moraine and remains only on the surface of the stagnant ice a short distance back from its front indicates an interval since the eruption sufficiently long for ice which then formed the neve to flow the whole length of the glacier and deposit its burden in the terminal moraine. Neither the length of the glacier nor the rate of motion of its different parts is known, but the time required for the transfer of material on the neve fields to the terminal moraine must be at least several hundred years. The time since the eruption has also been sufficient to permit the recession of the glacier front about 3 miles. The color of the waters of White River has been noted by all travelers on the Yukon who have passed its mouth. Schwatka describes it as resembling "a river of liquid mud of almost white hue," and McConnell says, "The turbid character of the White River is famous, and sufficient sediment is brought down to change the color of the whole Pelly Yukon flood from a pale green to a milky white." This turbidity has been attributed to the glacial source of the river, but glaciers could scarcely supply such an enormous quantity of mud unless acting under peculiar conditions. The presence of this great deposit of unconsolidated material, which is being ground up by the ice and removed by the young glacial streams, affords a ready explanation of the turbidity of the water. The highly vesicular character of the tufa permits a much larger amount of it to be held in suspension than of sediment derived from compact rocks. Tertiary volcanic activity. Evidence of volcanic activity, geologically recent though very much more remote than the eruption of the tufa deposit, is somewhat abundant. Perhaps the most striking example of such activity is seen in the basaltic mesa at the junction of Pelly and Lewis rivers. This lava flow took place after the river valleys had been eroded perhaps below their present levels and extended entirely across the valley. The river has since cut through the barrier, leaving only a few fragments of the basalt resting on the granite on the western side of the channel. This lava flow probably came from two or more vents. One, about 10 miles north of Selkirk, still retains the form of a symmetrical cone, and according to the native accounts has a small lake upon its summit, probably occupying the crater. A second vent was the high hill on the western side of the Yukon, about 4 miles northwest of Selkirk. Between the Yukon and St. Elias mountains black vesicular lava was seen at a number of localities, and north of the upper part of the White River are broad mesas which appear to be formed of black lava. These are all probably of Tertiary age. Glacial phenomena. Existing glaciers. So far as known, the existing glaciers of Alaska are confined to a narrow belt along the southwestern coast. Although the highest land lies in the coast belt, this is not the sole or chief reason for the notable absence of glaciers in the interior, except in so far as climatic conditions are thereby modified. There are numerous points in the Yukon basin from which practically all snow disappears in summer, although they have an altitude of from 6,000 to 7,000 feet and a mean temperature much lower than any portion of the southern coast. The explanation must be found in the very much greater precipitation and prevalence of clouds along the coast than in the interior. The glaciers furthest removed from the coast are those flowing from the mountains of the Wrangell group, where the moisture-laden winds of the North Pacific are able to pass up the Copper River valley and across the Coast Range, which is here much lower than toward the east. 4 considerable glaciers descend to or nearly to tide level on Taku Inlet and River, though only Taku Glacier, entering the head of the inlet, discharges bergs. A few miles up from the mouth of the river are 2 glaciers which come down into the valley nearly opposite to each other. Neither quite reaches the river, but, like the Norris Glacier on the inlet, they spread out into fan-shaped expansions with low wooded deltas of moraine material in front. Along the steep sides of the river valley above these glaciers a slight but distinct terrace has been cut about 150 feet above the river. It is probable that Wright Glacier, pushing across the valley to its northern side, dammed the stream for a short time after the main valley was clear of ice. Above Wright Glacier only a few small masses of ice or glacierets occur in the Taku basin in cirque about the higher mountain summits. No parts of the high interior plateau, either in the Taku or Yukon basins, carry glaciers, and probably very little, if any, snow remains throughout the year between the Coast and Cassiar ranges, though much of the surface is fully 3,000 feet above the snow line at the coast. The reason for this rapid rise of the snow line toward the interior is the dry climate, with short but hot summers prevailing throughout this region. In like manner, the high plateau east of White River is wholly free from summer snow, and the first glaciers seen in the Yukon basin were those flowing northward from the St. Elias range. Kluantu and Donjek rivers undoubtedly had in glaciers, but these were not seen since they lay too far east of the route traveled. 3 large glaciers flow into the White River basin west of the Alaskan boundary, and numerous streams crossed while following the southern bank of the upper White River rise in small glaciers which do not descend to the level of the valley. The largest glacier known to discharge wholly in the Yukon basin is one which lies approximately on the 141st meridian, called the Klutlan from the native name of the river to which it gives rise. Its source is in the great snow fields between Mount St. Elias and the high peak on the northern border of the range, called Nad Ajad by the natives. It extends several miles beyond the foot of the range, though it is rapidly receding at the present time, and is between 4 and 5 miles broad where it enters the valley. The stagnant ice at the front of the retreating glacier is buried under a great accumulation of moraine material continuous with the terminal moraine, so that it is impossible to determine the exact limits of the ice. The heavy mantle of vegetation which covers the terminal moraine continues a mile or more beyond the outer edge of the ice, becoming gradually less abundant as the active portion of the glacier is approached. The moraine in front of the Klutlan is the largest accumulated by any of the interior glaciers. It is composed very largely of the white volcanic tufa already described, but with this are mingled many angular fragments of amygdaloid lavas and a few of granite and gneiss. Much of the moraine has been removed by streams flowing from the glacier, but remnants 200 feet or more in thickness extend nearly across to the high land north of the valley. The second of the White River glaciers is about midway between the Klutlan and Scolai Pass. It is much smaller than the Klutlan and does not push out into the valley, but its front forms a wall of ice something over a mile in length from side to side of the narrow valley in which it lies. The third and largest of the interior glaciers flows from the high mountains northwest of St. Elias down into Scolai Pass, and from the divide sends a lobe of ice toward White River and a smaller one toward Copper River basin. This was named in honor of Mr. I. C. Russell, whose exploration and study of the St. Elias region during the past 2 years have added very largely to our knowledge of Alaskan glaciers and to the science of glaciology. The northern or White River lobe of Russell Glacier is buried under a heavy accumulation of moraine, bearing some vegetation, while the southern lobe is almost wholly free from moraine material, and the exposed ice has melted down to the smooth convex surface and feather edge characteristics of stagnant ice at the front of a retreating glacier. Taken altogether, the ice flowing northward from the St. Elias mountains is insignificant in amount when compared with that flowing southward. The Seward glacier alone probably contains a greater volume than all of those flowing into the White River basin combined. The great difference in climatic conditions on which the formation of glaciers depend is indicated by the difference in altitude of the lower limit of the neve snow on the north and south. According to Russell's observations about Yakutat Bay and my own on Prince William Sound, that limit on the seaward side of the mountains is at an altitude of about 2,000 feet, while on the north the altitude of the lowest neve observed was 6,300 feet. This rise in the snow line toward the north, over 4,000 feet in a distance of about 80 miles, is an important fact in the consideration of the causes of glaciation, either local or general. The Nizzenah River rises from one lobe of Russell Glacier, and in the upper part of its course is fed by a number of glaciers coming in from the high mountains on either side of Scolai Pass. One of these, the Frederica, possesses a peculiar interest in that it appears to be the only well-marked case among Alaskan glaciers of active advance at the present time. Flowing southward in a lateral valley which joins that of the Nizzenah at right angles, its front is parallel with the river and about 3/4 of a mile distant, the intervening space being a smooth gravel plain. The glacier terminates in a nearly vertical ice cliff stretching across the lateral valley a mile in length and about 250 feet high. Its surface is free from moraine, but is extremely rough and broken, wholly unlike the surface of stagnant ice at the end of a retreating glacier. At the foot of the cliff there is a small accumulation of gravel and ice fragments, apparently being pushed along by the advancing mass. Since the same climatic changes must affect all the glaciers of the region alike, the cause of this anomalous advance must be sought in some peculiar local condition affecting this glacier alone. A simple explanation is suggested, though it must be regarded merely as a suggestion since no means of verification are at hand. 10 miles to the westward of the Frederica another and much larger glacier flows into the valley of the Nizzenah. This is formed by the union of 3 separate streams, and of these the eastern appears to be retreating much more rapidly than either of the others. But this eastern branch probably has its source in the same basin as the Frederica glacier, and it seems not improbable that by some means the drainage of the basin has been diverted from the western to the eastern outlet, thus causing the rapid retreat in the former glacier and advance in the latter. The large triple glacier above referred to flows from the high mountains forming the eastern members of the Wrangell group. After the union of its three branches, the combined stream occupies the valley of the Nizzenah for about 6 miles, crowding the river out of its channel and forming a berg-filled lake above the ice barrier. Its great volume, together with the distance which this glacier pushes down in the valley, indicate an increased precipitation due to proximity to the Copper River valley, through which pass the warm winds from the ocean. No glaciers flow into the Chittenah valley from the ranges on either side, though all the upper portions of the Wrangell group are snow covered and doubtless the high ravines are filled with ice. Several large glaciers flow into the Copper River valley from the Coast Range, although its altitude is not so great as that of many portions of the interior plateau, which is entirely free from summer snow. The largest of these Coast Range tributaries of Copper River are Miles and Childs glaciers, named by Lieutenant Allen in 1885. Several others of considerable size higher up the river do not appear on Allen's map, probably because he passed up the river while the surface was still covered with snow. Miles glacier is quite comparable in size with those of the St. Elias region and is formed under essentially the same climatic conditions. It is evidently retreating at present, and the river spreads out in a lake-like expansion along its front in a part of the glacial channel from which the ice has receded. This expansion of the river is about a mile in width, and one side is formed by the glacier front, a cliff of ice 350 feet above the water and over 5 miles in length. Although the ice no longer reaches entirely across the valley, there remains a heavy lateral moraine indicating its former position and damming back the river as already described. The fact that the river has cut only part way through the moraine indicates a very recent recession of the glacier. Former glaciation. In common with other parts of the coast region, the Taku basin shows signs of intense glaciation from the westward moving portion of the Cordilleran ice sheet. Evidence of this in the way of glacial deposits is wanting along the lower portion of the river, while the polished and striated rock surfaces so abundant there may be due to the action of a glacier occupying simply the river valley. The evidence of an ice sheet becomes more abundant, however, toward the upper part of the basin. Thus, on a spur of the high plateau east of the forks of Taku River, boulder clay and stratified gravels were seen 3,100 feet above the river. The movement of the ice in the greater portion of the Taku basin was apparently in the same direction as the present drainage. The high broad valleys of the upper Taku branches are deeply filled with a mantle of boulder clay and gravel. In most cases this is spread out in a comparatively even layer over the surface, but also many narrow ridges occur from 10 to 50 feet in height, with a longer axis in the direction of the present valleys. These, however, probably mark a phase of deposition by a greatly diminished and waning ice sheet, so that they afford little, if any, indication of the direction of ice movement during the maximum glaciation. A much better indication is afforded by the transportation of boulders from the head of canoe navigation on the Taku to a point nearly halfway across to Ahklen Valley. Increasing numbers of boulders were observed composed of a peculiar granite containing large porphyritic crystals of black hornblende. At this point their source was found in a range of hills composed of the same granite, and no boulders of this rock were seen to the northeastward. At the summit of the divide but little evidence was seen which would indicate the direction of the ice movement, though it seems probable that it was toward the northwest, as it certainly was in Ahklen Valley. Some deposits of true boulder clay occur in various points along the lake, and a single occurrence was noted on the Teslin river about 5 miles from its mouth. Among the many lakes in the upper part of the valley are ridges and mounds of rounded boulders and gravel, which, with terraces of the same material about the head of Ahklen, were evidently deposited by a rapidly retreating glacier and the streams to which it gave rise. These gravels are younger than the boulder clay which they overlie, and also younger than the silt of the river bluffs toward the north. Among the most interesting deposits associated with the second period of glaciation in the northwest are those forming the river bluffs along the Teslin and other tributaries of the Yukon. Bluffs are continuous throughout the whole length of the Teslin river, increasing slightly in height from about 100 feet at the lake to 150 feet at the mouth, and frequently cut into a number of terraces. The materials of which they consist are light colored silts or fine sand interbedded with layers 1 to 3 inches in thickness of tough bluish clay. The layers of sand are often cross-bedded and contain sufficient clay to give the material considerable tenacity. At some places intermediate beds are highly contorted, while those above and below are undisturbed. Although the deposit differs widely from the true boulder clay, which it was seen to overlie, yet it contains occasional large angular boulders, evidently brought to their present position by floating ice. The bluffs are usually capped by a bed of coarse gravel, 10 feet or more in thickness, but sharply separated from the underlying silt formation. More rarely, layers of coarse sand and gravel a few feet thick occur interbedded with the silt, usually toward the top. This deposit undoubtedly belongs to the widespread white silt formation which Dr. Dawson has described as occurring at many localities in British Columbia and the upper Yukon basin. He regards the white silt as a deposit laid down in estuaries by waters containing glacial mud supplied by streams from the retreating or stationary ice front. The altitude of Ahklen is 2,500 feet, and hence the upper limit of the silt in the bluffs at the lower end of the lake is about 2,600 feet. The upper limit of the white silt, as observed by Dawson at various points in British Columbia and the Yukon basin, is between 2,400 and 2,700 feet, indicating a subsidence to that extent for a considerable period toward the close of the second epoch of glaciation. During this period of subsidence the present lake basin was doubtless occupied by a lobe of the retreating glacier which prevented the silting up of the portion of the valley so occupied. On its withdrawal at the close of the stationary period, the lake was left much as it appears at present, only somewhat larger, its waters being held by the dam of silt which had been laid down in front of the ice. Having in mind the conclusions of Dawson, McConnell, and Russell as to the northern limit of glaciation in the Yukon basin, evidence on that point was carefully sought in the plateau region southwest of Selkirk. For the first 125 miles the evidence was wholly negative. No sign of glaciation was seen, and this too in a country well calculated to retain the marks of ice action. The stream gravels consist of a very small number of rock species, and on following a stream to its head, the source of which was usually found, showing that no foreign material had been brought into their basins. While in general the surface contours are smooth and flowing, this is the result of long continued subaerial rock disintegration, and generally the surface rock is deeply buried beneath great accumulations of fragmental debris, though occasional sharp pinnacles and towers of rock project from the smooth talus slopes. Had this region been subjected to the action of an ice sheet during the glacial epoch, not only would the greater part of the rock debris have been removed, but the projecting pinnacles would have been planed down to rounded knobs, which would still retain polished and striated surfaces. Where Nisling river was crossed, its broad valley is filled with a deposit of coarse gravel and boulders, and from their great quantity and variety it was inferred that the stream had its source in a drift-covered region. The first undoubted evidence of ice, however, was found on the divide between Nisling and Kluantu rivers, where the northern edge of a sheet of boulder clay was passed. From this point southward the character of the surface suffers a marked change. It is no longer composed of the fragments of one or two kinds of rock occurring in place near at hand, but rather of many varieties confusedly mingled with clay and sand. The drainage system is imperfectly adjusted to the topographic surface, so that wide valleys carry small streams, and large streams like the Kluantu and Donjek flow, for considerable distances at least, through narrow valleys. The ice which has left its records in this sheet of boulder clay was probably a confluent glacier formed by streams coming from the south through narrow valleys now occupied by Kluantu and Donjek rivers. These valleys do not appear to have been glaciated high up their sides, and it is probable that those detached southern portions of the interior plateau already described were not wholly covered by ice even when the Cordilleran glacier had its greatest extension. The absence of a terminal moraine along the northern limit of the glaciated area would indicate that the Kluantu valley was filled by ice from comparatively small streams bearing little moraine material. Southward from the Kluantu valley records of former ice action continued to the coast, but the glaciation was by no means so intense as one might be inclined to expect from the high latitude of the region and the great altitude of the neighboring mountains. The marks of this former general glaciation have been removed from many of the river valleys, or at least greatly obscured by more recent glaciers which have but lately withdrawn from the valleys. It seems probable that at the period of maximum glaciation the relative amounts of precipitation on the northern and southern sides of the St. Elias mountains were much the same as at present, and then, as now, by far the greater ice drainage was toward the south. Some measure of the relative volume of the ice streams flowing in the two directions may be obtained from the relative amounts of moraine material which they have left. On the north, as already stated, there is no terminal moraine, only a comparatively thin sheet of boulder clay. South of the mountains, on the other hand, a deposit of morainal material, at least several thousand feet in thickness, was accumulated on the sea bottom in front of the glacier and is now shown, according to Russell, in the recent uplift forming the Chaix hills. Connecting upon the map the points which have been determined by various observers as the northern limit of the glaciated area in the Yukon basin, the position of the Cordilleran ice sheet at the period of its greatest extension is approximately outlined. Striated rock surfaces were observed by Dawson on the Pelly down to the point at which it crosses the 136th meridian, and on the Lewis as far north as 61° 40'. Although he does not regard these as strictly limiting points, still, in the light of facts observed on the plateau southwest of the Pelly Lewis confluence, the former at least may safely be regarded as such. McConnell and Russell consider the limit of glaciation on the Lewis to be near the mouth of Little Salmon River, and my own observations led me to think it is at least as far north as that. The point to which glaciation extends in the White River basin has already been indicated, with the evidence on which the conclusion is based. The extension of the line west of White River is less satisfactorily fixed than its eastern portion, depending on a statement of Lieutenant Allen that he saw no drift north of the Alaskan mountains, as he called the Tanana Copper River divide. The ice sheet, a part of whose northern limit is thus approximately outlined, had its principal center of dispersion in the high plateau of British Columbia between the coast and Rocky Mountains. From this center two subordinate lines of dispersion diverged toward the north and northwest, following the axes respectively of the Rocky Mountains and the St. Elias range, while the non-glaciated area formed a deep embayment in the Yukon basin between these divergent lines. The northern limit of glaciation is shown approximately on plate 18. It is probable, however, that many lobes from the main glacier extended down the valleys beyond the limit above indicated, while the confluent ice sheet was not sufficiently thick toward its northern border to override the greater inequalities of the surface. Thus the White River valley, at least, must have been occupied by ice well north of the general glacier front, even after a considerable amount of recession had taken place. The altitude of the valley at the mouth of the Nisling is about 2,400 feet, so that it must have formed an estuary during the period of subsidence marked by the white silt deposits, and the formation of Lake Wellesley is probably analogous to that of Lake Ahklen. End of section 20.